do like full screen. Kind of, no, that's kind of lame. All right, so 1.7 infinite limits. Let's do this. Where's my multicolored pen? 1.7 infinite limits. How's the volume on the mic? Is it okay? You okay in the corner? Can you hear me? Okay. So consider the function f of x equals 3 divided by x squared. That's what we're doing. You don't have this memorized. Next I did, but I don't. Well, where do you think we're going to consider function behavior? Where does this thing going to blow up? As x approaches what? 0. Not in the domain because we get 0 in the denominator. We want to know what is the behavior of f of x as x approaches 0. And before we consider that in a little more detail, I want to be very clear here that the issue here is different from that which we've seen previously. That if we were to try to plug and play here, we end up with 3/0. Remember the problem quotients that we had before? We ended up with what? 0/0. When we have 0/0, that's like just kind of like, hey, you're in trouble. The 3/0 or the constant over 0 actually tells us something a little more specific. We're actually in a better place in terms of knowing how this thing acts. And just to kind of give you the answer before we show the answer, what do you think happens as we divide 3 by increasingly small things? Well, so let's say we plug in 1, you're going to have 3. But then, like, if you have 1/2 and you square that, you get like 0.25. What's 3 divided by 1/4? 12. Oh, it got bigger. Yeah, just going to get big. Like, you take a small thing and divide it into a number, it goes in a lot of times. And the smaller you make that thing, the bigger the quotient gets. Okay, and so we're asking, well, we know we can't get to 0 because 3 divided by 0, and they release the nukes. But we can have an idea of, as we get super close to 0, this thing should be getting like massively big. But dividing something by very small values should give you very big values. And that's kind of, essentially where we're going today. And that's different than we had 0/0. Okay. So this is different. Note, this is a different situation. From those in section 1.5, for example. I really need a new doc cam. This like fuzziness is just unacceptable. Slightly better, maybe. I don't know. In 1.5, where we could manipulate f of x into a more limit-friendly form. qualitatively different. Let's see if we can support our hunch that this thing's going to explode towards really big values as we get close to zero. And so we're going to use the closer and closer method. Let's try closer and closer method. And we're going to do this from both sides of zero. So we're going to see what happens as we approach zero from the right and see what happens as we approach zero from the left. But first from the right. Fill out a little table here. X, f of x. Plug in 1 for x, you get 3. We can just kind of do this in our head. You plug in 0.1, you square it, you get 100th. 3 cut into 100th pieces is 300. Closer to 0, 0.001, or 0.01. This suddenly turns into 30,000. Adding a couple zeros each time. But the addition of this 1 0 turns into 2 zeros when you square it. You do 1,000th, end up with 3 million. We'll do one more. 0.0001 gives you 300 million. Yikes. 300 million a big number? For sure. Well, let's look from the left then. See if we see the same behavior. Use the same values. Actually, that's a lie. We're going to use different values, but we're going to see that the function gives us the same values. So from the left of 0, I don't know, start at -1. Well, -1, when you throw it into our function, 3 over x squared, behaves exactly like +1. As the -1 gets squared, divided into 3, shoots out +3. And all the way down the line, as we get closer to 0 from the left, you see the same function values emerging. This is an even function. It has symmetry about the y-axis. -0.01 gives us 30,000. -0.001, it's 3 million. And the last one, 0.0001, spits out 300 million. Oh, goodness gracious, you can't see that. There you go. So how, oh, how do we describe what's going on? Because as we'll continually see in our study of calculus this year, words are important. How we say things means things. Now, not a very coherent way to say that, but we need to choose our words carefully. Daniel. Are you Daniel?
Yeah.
Whew.
As x approaches 0, f of x gets like closer to infinity.
Not a bad first attempt. Okay. As x approaches 0, f of x, would you say, gets closer to infinity? Jack.
Would it approach positive infinity?
Oh, so there's some different infinities. Okay, yeah, that would be nice to say positive. Van Humesen.
As x approaches 0, there is no limit.
Okay, we're trying to say a couple things at once. There's some good stuff being thrown out. First, yes, we are getting closer to positive infinity. Okay. Question, are we ever going to get to infinity? No, it's kind of like a cat, you know? Closer you get to it, it scampers away. The little closer, scampers away. You're never going to get it. Okay? I guess some people do catch cats, but I don't know. You never arrive at infinity because that's the nature of infinity. You can always add one more. And so what, is it Kate or Katie?
Kate.
Kate, Kate's 2 in first grade, is also valid that this limit does not exist because you can't get there. You are trying to get there, but you're never going to get there. And so the language we're going to use here reflects basically everything that those 3 students just said. So we're going to do a big old bracket here, kind of encapsulate, I don't know, everything that was just said. So in this situation, let's change color here, it's a little monochromatic for my tastes. In this situation, we say that f of x and here's kind of the, calculus phrase, increases without bound. As x approaches 0. Or, and this is sort of stealing some language that we haven't spent too much time with, but that I'm planning to have us spend some time with before the end of the chapter. An equivalent thing would be to say that we can make f of x, the function values, the outputs, as large as we please, as big as you want them. By making x sufficiently close to 0. By making x sufficiently close to 0, keeping in mind we're never going to get to 0 because 0 is not in the domain of our function. But say you want 300 million is not enough, you want 300 trillion. There is a number close enough, if we go close enough to 0, that will give us that function value. Furthermore, notationally, we can write the following 3 statements. I'm going to write this first and then say it. And kind of model for you how I never want you to say it. And I wish we had kind of different notation we could use here. I know that there's an equal sign here. And so we want to say, oh, the limit of f of x as x approaches 0 from the right equals positive infinity. Never want you to say that because that puts it in your brain that this thing exists. When you see this, I want you to say, hey, f of x increases without bound as x approaches positive infinity, or as x approaches 0. And we can repeat this as x approaches 0 from the left. That was this table told us that. Approaches positive infinity, increases without bound, however you want to say it. And then from both sides, just as x approaches 0, the function increases without bound. However, despite what we just wrote here, we need to be just like as crystal clear on this as possible. These limits do not exist. They don't. They DNE. However, please be clear. Writing in red, getting your attention, hopefully. These limits do not exist. Instead, we borrow this language and say f of x increases without bound or it's appropriate to say approaches positive infinity. As x approaches 0. I know this looks like it's saying that these things equal infinity, but they don't. They do not exist. So all three limits, D and E. This is a statement about the behavior of your function, not an equivalency about what this thing is. Can't be equal to infinity. Grabbing the wind. That's a better analogy. There you go. Can't hold the wind. Unless you gotta sail, I guess. Dang it. Gotta work on my analogies. What does this mean for a graph? Let's bring this back to math, graphs. Where's my straight edge? I'm already taking my favorite straight edge. Oh, that almost ended poorly. Here's scissors. I guess we'll use a popsicle stick. Sure, why not? That'll work. Straight edge. A nice clear bit off my desk. I am miffed. So what does this thing look like? Let's graph it real quick. This is going to be a very non-rigorous graph. We're just going to kind of give you the idea. Whoa, what's going on? What's going on? So basically, it looks like this. Both the left and right. I guess we could have done it on our graphing calculators, but we'll make a little note here. What does it kind of appear is going on at x equals 0? Like a fun word. What was it? I heard it. Asymptote. One of your favorite words to say and spell. Appears to be a vertical asymptote. Asymptote. Gosh, that was fun. At x equals 0. We'll revisit that idea after we've danced around a little more with the vertical limit idea. Okay. And just note, like, a little like finger approach thing here, like this is different than like they're approaching different actual values and just not meeting. This is like your fingers are being like ripped up to positive infinity, and it's just like you're dismembered, disemboweled. Maybe you get disemboweled too. I don't know. It's a weird limit, okay? But it's different. It's like built into the very nature of this function. There's no fixing this. We're gonna see tomorrow, Thursday, that sometimes when we've got these breaks in our graph, we can fix it. You ain't fixing this. That's what the graph looks like. There's a break there, okay? Okay, questions about approaching positive infinity? Do you suppose that if we can approach positive infinity, we can also approach negative infinity? Well, let's see what that looks like. I'll give you a hint. Here's what it looks like. See this? See this? It's gonna look like that. Oh, should we just skip the next one?
Yeah.
No. Okay. But that's basically what we're doing. Not basically, exactly. Because now we're gonna consider, now we'll go a little more swiftly through this. 4K, it is just the literal flip side of what we just did. We're gonna consider the function, still call it f of x. But now it's gonna be the opposite of 3 over x squared. Using our tried and true closer and closer. Use the same table values and see what happens. I just told you what happens. It's going to give us all the opposite function values. So from the right, plug in a 1. 1 squared is 1, divided into 3 is 3, but then we hit it with the opposite, it's negative 3. How about a 10th? A 10th squared is 100th. 100th into 3 is 300. Then we hit it with negative 300. Oh, these values look familiar because they're the exact same values from the last page. We're just flipping them. Same thing with 100th becomes negative 30,000. 1,000th, negative 3 million. And finally, a 10,000th turns into negative 300 million. Numbers get pretty small. You know, it's kind of one of those mind-bending things about negative numbers is like, this number looks a lot bigger than negative 3, just because it's longer, but it's smaller. It is so much further that way. Why am I pointing that way? My number line. Like negative 300 million is like out the door, over the field, past PCH, into the ocean, probably past Catalina. It's way smaller than 3. So even though these numbers look like they're getting bigger, we're getting a lot smaller. That's from the right. Maybe something different happens from the left. It doesn't. But we're going to verify. I think the number line is woefully underutilized as a tool for picturing math. Numbers, man. Ground line. I know. Okay. Negative 1 gets the same treatment, becomes a positive, gets divided into this negative number, gives you a negative function value. Oh, there's going to be another even function that mirrors these positive inputs. You betcha. Negative 1/10 gives you negative 300. Negative 100th gives you negative 30,000. We have seen this song and dance before. Negative 3 million. And caramba. And finalmente, negative 300 million. Yikes. So somebody not named Kate Japper Dan. What language do you think we're going to use to describe this situation? What is f of x doing as we approach 0 here? Power.
We can make f of
x sufficiently smaller as we approach it? As x approaches zero?
I appreciate the effort, a little bit mixed up with the language, but, Lenthal, decrease without bound, that's one way to say it. Somebody want to try to jump into where Jackson was trying to say? Sweeney,
We can make f of x as small as we please by making x sufficient.
beautiful, so I think you mixed up the sufficiently part, okay? So we can say that x decreases without bound, that f of x decreases without bound. F of x approaches negative infinity, but never gets there. Or, to sum it up, that we can make the function values as small as we please. Again, negative 300 million is a small number. And we can make it even smaller still, so long as we take x sufficiently close to 0. Okay? So we're basically going to write the exact same thing as we did on the previous page, but now replace large and small and negative and positive. So in this situation, we say that f of x decreases without bound. I don't know why I just put decreases in quotes. Let's do decreases without bound, all in quotes, as x approaches 0. Or what Power and Sweeney helped us get to is we can make f of x as small as we please, not as large now, but as small as we please, by taking x sufficiently close to 0. Again, remember it's not equal to 0. Because just as we saw in the previous example, 0 is not in the domain of this function. Get really, really close to it, can't be it. And then in the same manner as we did with increasing without bound or approaching positive infinity, we can steal this limit language to indicate that. Say that, hey, if we approach 0 from the right, f of x is going to decrease without bound. F of x decreases without bound as x approaches 0. I'm not saying that the limit of f of x equals negative infinity, because it doesn't. It's just like the best we can do with our notation. Or that the limit, or rather the function f of x approaches negative infinity as x approaches 0 from the left. And then finally, the function decreases without bound as x approaches 0. Just as on the other side, we need to be super clear. All three limits here do not exist. Despite these statements we're writing that appear to say that they equal negative infinity, they don't exist. Limits do not exist. And that's just so crucial that we embed that into our brains. We're going to write it again in red. Again. We have to, yep. These limits do not exist. Instead, we say f of x decreases without bound or approaches negative infinity. As x approaches 0. Whew. Work some different muscles when you're doing it pen and paper as opposed to the whiteboard. Is the pain you guys feel? Here she does more often. Feel your pain. I have to do it twice. My life's harder. But Mr. Smith, you get paid to do this. Oh yeah. Laugh all the way to the bank. What's the graph look like? Well, it's just the flip version of what we did on the back side. She got paid yesterday. Teachers get paid once a month. We actually only get paid 11 times throughout the year. And so yesterday was the first time since July. No. No. Yeah. You do not get a paycheck on July 30th. So you get paid in June because you work in June. You don't get paid in July because you don't work in July. You get paid in August because you work in August. And some people make a pretty big fuss about that, but you know it's happening. So figure out your monthly expenses and set aside that month as the year goes on. They even have this cool tool on the bank that most of us belong to, Schools First. Any Schools First members here? Gandhi's, I can see that. Van Humiston, where they literally just say, hey, this is how much money I want for the 12th month where I don't get paid. And they just take it out of your paycheck every month. And then in that 12th month, it's there. Adult stuff, you know, it's confusing. Anyway. So this seems, Dan.
Instead of putting the equal sign, why don't we put an arrow for like as it approaches?
That's not what we do. It'll make more sense though. Yeah. And you would still sort of run into the same issue that like, oh, the limit is like approach. The limit just doesn't exist. Okay. So we're shortchanging ourselves with the vocabulary we have available to us with the notation. But ultimately, we just need to be able to see this and know, okay, that's just telling me that the limit doesn't exist, but telling me a very specific thing about how it doesn't exist. Because we'll see it by the end of the lesson that when we see this, it's going to tell us graph behavior, or we already saw it. And these ones were kind of nice because they were the same, but the example we're about to do, from one side, the function increases without bound, which tells us something about our function. From the other side, it decreases without bound, which tells us something else about the function. So these are still important in terms of telling us what your graph is doing. They don't exist. All right, so this seems, you know, kind of labor intensive, the closer and closer thing. So we need to establish some sort of framework for looking at these infinite limits and seeing what is happening here. Because if we have to do closer and closer every time, no thank you. So let's do an example where we kind of start to, I don't know, cultivate that framework. And so this will be an illustration, it's not a full example. Hasn't grown its wings just yet. We'll call it illustration 1 because why not? The plan is to get through illustration 1 and then maybe give you a quick smoke break and then carry on. At least that's what we did in first period, worked out okay. So consider, I love that, consider, contemplate, think about it. Consider, who just sits around and considers functions? Consider dos equis divided by equis menos uno. What are the limits of f of x as x approaches, where do you think we're gonna be asked to approach? 1 from the right. And the limit of f of x as x approaches 1 from the left. Well, first of all, how should we approach like every limit that we ever bump into on the street? What's our first move? Plug and play. Let's just see what happens. Maybe we get lucky. Maybe this is like, just works out. I mean, we have a pretty good sense that it won't work out because that denominator, but you never know. Plug and play. Limit as x, let's just say positive 1. I don't know. Or 1 from the right. Try to plug and play. We go 2 times 1 divided by 1 minus 1. Yo. We end up with 2 over 0. That's not good. But this is different than 1.5. This is not 0 over 0. This is not a big middle finger. It's like a small middle finger. Okay. You can deal with the small middle finger and figure it out. 0 over 0 is just like, you got a lot of work ahead of you. When we get to this point, we're like, we don't feel it yet. We haven't seen how to do this just yet. But we're like really close to like being able to say what the answer is. 0 over 0 is just like, can't help you until you help yourself. You got some work to do. This is closer. And we're going to find out right now how we're going to do this. First, we're going to do closer and closer just to kind of see what appears to be happening. And this will hopefully be the last closer and closer. You might have 1 or 2 on your homework, actually. Last one we'll do together anyway. And we'll look at it from the right. And we'll look at it from the left. So we'll do a little table from the right. We need like 5 values, sure. 1, 2, 3, 4, 5. f of x, left. f of x. So we're approaching 1 from the right. What's something that's like bigger than 1, but kind of close to it? 2. Sure. Plug in a 2 there. 2 times 2 is 4. Divided by 2 minus 1, that's like 4. All right, cool. That's still not very close to 1. How about like 1 and a 10th? 1.1. Well, what's 2 times 1.1? 2.2. What's 1.1 minus 1? 0.1. So 2.1 divided by 10th is like 21, 22, 22. Sure. Wait, who said 2.1? It's 2.2. Did I say 2.1? Why don't you yell at me? 2 times 1.1 is not 2.1, it's 2.2. You call yourself calculus students. Keep it going. What if we want to do like 1.01? I'm just going to tell you, this turns into 202. That's kind of fun. How about 1.001? 2002. We had a sad moment in first period when I realized that I have very fond memories of the year 2002, and none of you were born. Oh. Okay. 1.000. Actually, let's be real. 2002, I was an 8th grader. 8th grade was not a hot year for me, so not fond memories, but I do remember it. Okay. If we're honest, we could just like strike the middle school years from the record for all of us, and we'd probably all be happy, healthier, more well-adjusted people. But that's my personal opinion on the matter. Anyway, 20,002. Okay. What the heck is happening here? Getting bigger. Do we have more precise language to say getting bigger? Do we have more precise language to say getting bigger? It is increasing without bound. Cool. or at least appears to be. From the left, let's consider. Well, we want to be from the left of 1. Let's start like 0. That's 0. How about like 0.9? What is 2 times 0.9? 1.8. What is 0.9 minus 1? Negative 0.1. So then a positive 1.8 divided by a negative 0.1 gives you a negative 18. The negativity of this function value comes from this negative difference here. That because we're choosing values slightly less than 1, something slightly less than 1 minus 1 gives you a negative number. And that will continue as we choose exceedingly closer numbers to 1. Okay, now this is still negative. 0.99 minus 1 is negative 0.01. And we get negative 198 when we do the quotient. 0.999, negative 1,998. And finally 0.9999, negative 19,998. The positivity or negativity of these function values was determined by the fact that we were coming from values smaller than 1, meaning that these values all stayed negative. They get really close to 0, but they're still negative. Here we were getting really close to 0. They were positive. So that determined the nature of our quotient there. What is the fancy language we have to describe our approach to 0? Sorry, our approach to 1 from the left. What is our function doing? Decreasing without bound is approaching what number or what idea? Approaching negative infinity. Okay. But again, if we have to do this every time we want to evaluate a potential infinite limit, we'd be like, nah, I'll pass on that. Darn tootin'. So let's see if we can kind of formalize this little arithmetic that we just verbalized about the nature of this approach to 0, because that's going to be the determining factor in all these problems. What kind of numbers on top? What kind of 0 is on bottom? And what does their combination tell us about what our function will be doing as we approach 0 on the bottom? So to put this kind of in a very simplified form, we're going to look at this briefly analytically, and then sort of after our break, give you the full framework for how to do this. So, same example, but we're going to come at it analytically. First, from the right, the limit of f of x as x approaches 1 from the right. Just to get an idea here, and I'm just going to warn you, this process is going to feel maybe a little unscientific and a little imprecise. But this is how we do it, okay? This is how we do it. Choose a value close to 1, but bigger. Okay. So let's do 1.1. So we'll do 2 times 1.1 divided by 1.1 minus 1. As we noted, this turns into 2.2 divided by positive 0.1. So it turns into 22. So the positivity of this quotient leads us to believe that this function will continue to increase without bound as 1 gets closer and closer as x gets closer and closer to 1, and that this bottom gets closer and closer to 0. But to put this even more kind of just basically, as we approach 1 from the right, what is the product on top going to be in terms of a positive or negative number? Always? Yeah, because even if it's 1.000000000000001 times 2, that's still a positive number. Got a positive constant on top. No matter how close we bring x to 1, even 1.0000000000000000001 minus 1, eventually, like, yeah, it's like, it feels like it's 0, but it's still just the tiniest bit positive. It's the tiniest sliver of a positive number. And if you've got a positive constant divided by a positive 0, what kind of infinity are we going to be approaching? Positive. Just kind of basic arithmetic at this point.
That's supposed to be a 1 or a positive sign. Zero.
A positive sign. This is kind of indicate, okay, our 0 here is we're approaching 0 from positive values. Probably the better way to say that. Well, from the left side, we can do a similar song and dance and arrive at a different conclusion. We're going to choose a value close to 1, but smaller. Like 0.9. So 2 times 0.9 divided by 0.9 minus 1. Now we're getting our 1.8 on top. Now the bottom turns into a negative 0.1. So this quotient turns into a negative 18. Indicates that we'll probably be decreasing without bound here. Sort of the background music here is a similar comparison as we did up here. No matter what number we put as the one close to 1, the top is going to remain positive. 2 times 0.99999999999999999999999 is positive. However, that same 0.9999999999999 minus 1 is going to be a negative number. An ever so slightly negative number, but still a negative number. And so we would indicate, okay, this bottom 0 is approaching 0 from negative values. And that combined with this positive constant on top gives us the kind of backup we need to say, okay, this is going towards negative infinity. Positive divided by negative gives you a negative. And after our break, we'll kind of see the theorem. And this is exactly what we're going to do. We're just going to say, okay, what kind of numbers on top? Where are we approaching 0 from? Make the call. And there's 4 possibilities. Positive, 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 negative, negative, positive, negative, negative. There's the rest of the lesson. Okay. I got 11:05. At promptly 11:10, we will continue. If you have snacks you need to eat, do them in the hall. But do not chatter too loudly out there. You can chatter as much as you want here. If you want to check your socials and all that, you know, now's a good time. Or if you need to go to the bathroom, figure it out. You guys are smart.
What time did you say you had?
11:10. 5 minutes.
Yeah, I just, it's done, right?
Most of them.
Guidance, but. Elevation.
It's like it's tight. Yeah.
Yeah.
So the closest ones near us are of course Hanson Center. If you've ever heard of those, that's surf spots.
I had
That's an elevation for yeah. Yeah.
All right, all right, all right. Where does the time go? I don't know. But I got 11:10. Means es la hora para aprender más. Siempre es la hora para aprender. En este clase. Sí. No es la hora para hablar. White kid's still talking. Not the hour to talk. I got that gringo Spanish, don't you worry. Okay. So we are going to formalize to some oh, is it locked? Oh, that's weird. So this process is literally how we're going to do infinite limits. We're going to ask ourselves, what kind of numbers on top? What kind of numbers on bottom? Which infinity are we approaching? So once we've found ourselves in a constant over zero plug and play situation, which again is different than the indeterminate 0 over 0 plug and play situation. We'll see sometimes one leads to the other. Sometimes 0 over 0 leads to this. But once we've arrived here at a constant over a 0, we're now into this mindset where, okay, what kind of infinity are we approaching? If you divide 0 into a number, you get infinity of some sort, okay? Or you approach infinity. You can't actually do that final division. And so, like I said before the break, there are 4 distinct possibilities here. We're going to write down all 4 as part of 1.7.4 theorem. And this is actually limit theorem 12. What happened to limit theorem 11? We don't talk about limit theorem 11. Actually, we'll probably talk about it at some point, but for now, we're going straight to 12. Here's what limit theorem 12 says, that if A is a real number, and if the limit of some function f as x approaches this number A is equal to 0, and the limit of some second function, g, as x approaches that same number A is equal to c, which is some non-zero constant, remember, if c is a constant, if c is 0, and you end up with 0 over 0, that's a fish of a different color. But if 1 is a constant and 1 is 0, then there's 4 possibilities. Constant, non-zero constant. Constant, no. Okay. There's 4 here. First, if c is a positive constant, greater than 0. And if f of x approaches 0 through positive values, then the limit of g of x divided by f of x as x approaches A does not exist, but that quotient increases without bound. Now, I already forgot what G and F and all that baloney is. So we're going to do kind of an addendum to this theorem as we go. Just to remind ourselves, this is really simple. Let's not make this more complicated than it needs to be. So up to the right, kind of in some brackets, here's what's happening. The limit of G of x is C. And we just said C is positive. We got C. The limit of f of x is 0. So we plugged and play and we got to constant over 0. But we're like, well, what type of infinite limit is this? Well, by doing a little detective work and discovering that C is a positive constant and that we are approaching this 0 from positive values, what this says, C is positive, F of x approaches 0 through positive values, now we conclude, oh, positive divided by positive, we are increasing without bound. We are approaching positive infinity. This is the clearest way to think about this. So that's what we're going to do. There we go. The second possibility, little I. We're going to keep C positive, but now f of x is going to approach 0 through negative values. Cool. Let's actually do this part first, the parenthetical. I guess it's not technically a parenthetical because they're not parentheses, but you get my meaning. Still C over 0. So plugging and playing, these two situations would look exactly the same. You end up with C over 0. And furthermore, you'd end up with a positive C over 0. And so you will have to do a little work to figure out this second part, that f of x is approaching 0 through negative values. Which tells us that this quotient is decreasing without bound, approaching negative infinity. So in the language of limit notation, this looks like g of x divided by f of x approaches negative infinity as x approaches a. Truth of this is determined by this relationship here. That a positive number divided by a negative number gives you a negative number. That's 2. So there was 4. Let's go. Little I. So we've done both situations where the constant is positive. So let's flip that around and say, okay, now if C is less than 0, if C is negative, and f of x is approaching 0 through positive values, C negative approaching 0 through positive values. Let's map out in our brain before we write the actual conclusion. Again, you just get a constant over 0 when you plug and play. So you need to dig a little deeper. Now our constant is negative. And since we just said we're approaching 0 through positive values, we're going to do 0, a little plus sign. Where does this situation send us towards? Negative infinity. We've got a negative constant divided by a positive minuscule number. Negative infinity. And so in limit notation, g of x divided by f of x approaches negative infinity as x approaches a. We've done positive, 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 negative, negative, positive. What's left? Negative, negative. Where do we think that's going to go? Positive infinity. So still a negative constant. C is less than 0. And now f of x is approaching 0 through negative values. Start with our parenthetical. That's where I was looking for earlier. Somebody first period told me it was in a positive. What's in a positive? like when you say like, you write Mr. Smith, comma, my calculus teacher, comma, tells really funny jokes. What is the my calculus teacher part called? An appositive, okay. So I was kind of saying that these were like appositives, but I think I like parentheticals better. The positives kind of a weird word. Anyway, you get a constant over a 0. In this case, our constant is negative. Our 0 is approaching 0 through negative values. We got a negative over a negative. I'm thinking that's going to send us to a positive infinity. Yep. So then the limit as x approaches a of g of x divided by f of x do not exist, but that quotient increases without bound, approaches positive infinity as x approaches a. Whew. Are you ready to do some perfect examples? Yeah. Yeah, you are. Let's do some. We got 2. Then we got one more definition, and then we're done. 11:22. What time is pod time? 43. That might be cutting it close, but we'll try. Okay. This will be example numero uno. Is f of x equal to x squared plus x plus 2? Divided by x squared minus 2x minus 3. First things first, I want to plug and play and see what happens. Because maybe we luck out and this just turns into a number and we're like, sweet. And I'm not very confident that's going to happen because that would kind of defeat the purpose of having it as an example, but you never know. So plug and play. Oh, but they want, I didn't tell you where we're approaching. 3. So plug and play with 3. 3 squared plus 3 plus 2 divided by 3 squared minus 2 times 3 minus 3. 3 squared is like 9 plus 3 is like 12 plus 2 like 14. Cool. Maybe we're gonna get lucky. Maybe it's gonna be a number. What's 3 squared? 9. Minus 2 times 3, that's 6. So 9 minus 6 is like 3. 3 minus 3, oh, dagnabbit. But we know that we are in an infinite limit situation. We just got to figure out which kind. So we're happy about that. We have learned something about this that we would not have known if this just turned out to be 0 over 0. Okay. So we're in a healthier spot. And we're actually going to now figure this out. And with infinite limits, you will always need to do this from one side or the other. Okay, because you got to figure out, that positivity or negativity of your 0 is going to be determined by what side. So even though it says the limit of f of x as x approaches 3, we have to consider 2 things. We have to consider this limit as we approach 3 from values bigger than 3 and smaller than 3. So let's start with from the right. We'll call this part A. Well, first, actually, let's notice that f of x equal to x squared plus x plus 2 divided by x squared minus 2x minus 3. The top you're kind of stuck with. That thing won't factor. No real roots. I guess that's not fair to say. The beauty of polynomial functions is that every single one of them is going to factor. Every single one. Just not all of them are going to factor into real factors. Okay, these ones would have some complex numbers involved. The bottom one is nice though. Turns into x minus 3 times x plus 1. Nothing cancels out, but it's just kind of nice to play with here and to see this. And will help our approach in finding what the limits or what the function is doing as we approach 3. So the limit of f of x as x approaches 3 from the right. We turn this into a plug and play situation, but with an eye towards this up here, trying to identify which of our 4 possibilities we are in. So we plug and play. We do 3 squared plus 3 plus 2. And I want to use this form of what we're doing because I think that makes more clear why we get to where we get. There's going to be 3 minus 3 times 3 plus 1. Now we know from what we just did up here that this numerator turns into 14. And from just looking at this, we know that 3 minus 3 is 0. And so this bottom turns into 0. Just did this. Our job is to make some decision about what kind of 0 we are looking at as we approach 3 from values bigger than 3. And so we're going to look at this bottom product and just ask ourselves, what is the value of 3 plus 1, regardless of where we approach 3 from? 4, or it's positive is probably a better way to put it. This 3 minus 3 though, approaching from numbers slightly bigger than 3. What kind of value is that? Should be positive, right? Like 3.0000000000001 minus 3 is a positive 0.0000001. Which leads us to believe that this bottom 0 is approaching 0 through positive values. And it's determined by this guy right here. Approaching 0 through positive values. So a positive constant divided by a positive 0. From the right side, we are increasing without bound. Yes.
Go over again how you said it's approaching from positive.
Yeah, so I looked at this part of our quotient. The top part, it just evaluates to 14. Doesn't matter which left, right, bottom, top. This bottom part, when we just plug in 3, it goes to 0. But we know that we're not actually allowed to plug in 3 because it's not part of this function's domain. So we're doing like in our brain, kind of the closer and closer approach with the table and saying, okay, I'm not actually allowed to plug in 3 here where it says x minus 3. I can just try to get super close to 3. And from the right, those super close to 3 values are like 3.2001 minus 3. And that 3.2001 minus 3 is a number that is ever so slightly bigger than 0. It's like 0.0201, but still positive. So you have to kind of look at what the limit is telling you. Okay, I'm coming at 3 from values bigger than 3. I'm subtracting 3 from those slightly bigger than 3 values until this is positive. Yeah, and that's the crux of the problem, is making that decision. We'll see from the other side now, and I'll try to be a little more deliberate showing this. So from values to the left of 3, slightly smaller than 3, we repeat this process. We plug and play. we get 14 on top, because it's still just essentially 3. And on the bottom, we get the same product, 3 minus 3 over 3, or times 3 plus 1. But again, this is not actually 3 that we're plugging in. We can't plug in 3. So we have to ask, oh, I'm sorry, this should be a left. That should be a negative sign. X approaches 3 from the left. Write that. X approaches 3 from the left. From values slightly smaller than 3. So remember your name right here. Jack. So now we're looking at the same difference here. This 3 minus 3, it looks exactly the same. But now we're telling ourselves, this isn't actually 3. It's really something like 2.999999. Tell me, Jack, if we take 2.999999 and subtract 3, what kind of number do we get? A negative number. Okay. And so now this tells us, because this difference is approaching 0 through negative numbers, this sort of determining quotient at the end becomes a positive 14 still. It's still positive 14. But now this 0 we've determined is coming at 0 through slightly negative numbers. Which tells us that from the left of 3, we are decreasing without bound. And what we'll see at the very end of this lesson, once I give you the definition, that this tells us there's an asymptote at 3. Might be other stuff going on with this function, but for sure at 3, there's this do not cross sign. From the left side, we're going like that. From the right side, we're going like that. And again, both these limits don't exist. And for sure, this limit does not exist. But you kind of got that nice, both the missing fingers and you're being dismembered as you go. Jack.
So if the other turned into log, like the 4 part, that one's -4 instead.
Okay, so this will definitely come up, and Jack is asking, so what if this had factored into, yeah, x minus, no, 4 minus x? That we want? No, -4 plus x. You do have to take that into account. You have to take the entirety of that bottom part into account. So if this had turned into a negative number, the negative times the positive would have given you the -0 here. The negative times the negative would have given you the positive 0 here. So we'll flip it. I don't know off the top of my head if your homework problems have anything like that. I think they stay pretty standard where you're just considering the one factor. But I guess we'll find out when we start doing it. Okay, let's do a second example. Second and last, and then I'll give you the definition of asymptotes. Whew. Don't think we're going to finish before, yeah, probably not. Go very briefly into pod time. Okay, example 2 is kind of like a nice review of like, hey, this is how hairy limits can get. And these are the thought processes we go through. So example 2, we're going to start with a plug and play that leads to an indeterminate example. Yeah. But then eventually with some finagling gets us to an infinite limit. What limit? Why is there an A here? I don't think we need A. we'll just say the limit as x approaches 2 from the right of the square root of x squared minus 4 divided by x minus 2. Yuck. No me gusta. Ladies and gentlemen, what is the first thing we do with any limit problem? Plug and play. See what happens. We plug in a 2. 2 squared minus 4 divided by 2 minus 2. Yuck. Get the square root of 0 divided by 0. Which looks a lot like 0 over 0. So this is the big middle finger. This is the, I'm not telling you anything. You gotta do some work. Because this could go a variety of ways. We've seen these indeterminate forms in 1.5 where with a little finagling, there actually is a limit here where it turns into a quarter or turns into 7 or whatever number it turns into. It's just disguised. We don't know which way this is going to turn. We have a feeling it might turn into a non-existent infinite limit because we're in 1.7 infinite limits. But if this was your test and I just said evaluate this limit, you wouldn't know. You'd just be like, oh, indeterminate. I got to do some work. So you roll your sleeves up and you get to work. We know we got to do some work to like get rid of the 0 over 0. Or to put it another way, because this is 1.7, if we're trying to do theorem 12, we need a constant on top. Okay. So in order, or actually, no, I'm not going to say that. We're just going to finagle, official math word, to determine if limit exists or if it is an infinite limit. Right now, we don't know. Well, the finagling we're going to do, I don't know, we don't like radicals, so let's try to get rid of the radical. So the limit of the square root of x squared minus 4 divided by x minus 2 as x approaches 2 from the right. Well, we need to multiply by 1 here. What should our 1 look like, Daniel?
Version of x plus 4, x squared plus 4 over.
We're thinking too hard. This is actually not a conjugate problem. I know we see square roots, we're like, oh, conjugates. The conjugates deal with a plus b. We just want to get rid of the radical bummer.
The same thing.
What's the same thing as the top?
Square root of x squared minus 4.
We just multiply by square root of x squared minus 4. That's gonna poof, get rid of the radical symbol. But we can't just do that. We gotta multiply by 1. So we're also gonna do the bottom by x squared minus 4. And now this is just 1, and that's fine and dandy and well. And so this turns into the limit as x approaches positive 2. On the top, the square root of x squared minus 4 times the square root of x squared minus 4 looks a lot like x squared minus 4. On the bottom, because we're lazy and it would be scary to do it, and because it actually is the right thing to do, we're not going to try to multiply this out. We're going to keep this as x minus 2 times square root of x squared minus 4. Okay. Let's do some factoring. Because I definitely have this kind of spidey sense saying, ooh, x minus 2, x squared minus 4. Oh, there might be a pathway to success in there. So as x approaches 2 from the right, we're going to write x squared minus 4 in its factored form of x minus 2 times x plus 2. Ooh, mama. And we get divided by x minus 2 times square root of x squared minus 4. Do we want to cross something out? Do we want to cross something? Yeah, we want to cross something out. What do we want to cross out? X minus 2. And in general, if we're working a limit problem and we get to a point where we cross stuff out, that would probably be a good moment to then, well, first see if there's anything else we can cross out. But once we determine that we don't think there is, try to plug and play it again and see if your situation has improved. Because we've changed the appearance of this function in a way that might be beneficial to discovering the limit at this point. And so we'll do that. Now with this new form of our function, we're going to plug and play. And we're going to say, okay, we've got 2 plus 2 divided by the square root of 2 squared minus 4. Up top, we've got a 4. Okay, that's an improvement. It was a 0 before. Down below, we've still got 0. But this is an improvement in our situation. This was the big middle finger. This is kind of just a smaller middle finger. Like, okay, we can figure this out. Because now we know that we're dealing with an infinite limit. We just have to figure out what kind. And so to do that, we're going to consider this difference right here. This difference right here. Recall, we are approaching 2 from values ever so slightly larger than 2. When you square something ever so slightly larger than 2, how does the result compare to 4? Ever so slightly bigger. And so when we take a number ever so slightly bigger than 4 and take 4 away, you have a positive number. So this here is a small positive number. Meaning that this 0 is not actually a 0. It's the most minute, tiny little positive number. When you take that little minute positive number and divide it into a positive 4, what is your function doing? Approaching what? Positive infinity. Oh, happy day. So if we wanted to, put this into a little word sentence, I guess most sentences have words. As x approaches 2 from the right, f of x increases without bound. Limit does not exist, but the function we know now from the right of 2 is going to increase without bound. Questions about example 2? There are some theorems on, I don't know what pages. I think they're theorems 1.7.5 through 1.7.7, and they deal with adding, and multiplying infinities. And we're not going to write them down because they're kind of burdensome to write down. But your intuition is going to serve you here. If you take infinity and you add a constant to it, what are you going to get? Infinity. If you take negative infinity and add some constant to it, what are you going to get? Negative infinity. If you take infinity and multiply it with a positive number, what are you going to get? What kind of infinity? If you take a negative infinity and multiply it with a positive number, what are you going to get? How about a negative infinity with a negative number? Positive routine, okay, you guys got it. So that's theorems 1.7.5 through 1.7.7. The stuff that I do want you to write down is the definition of a vertical asymptote. This is the last thing, and then I'll stop talking, and you guys can, sit quietly in the night. Sit quietly in the night, I don't know what that means. Sit quietly for the rest of the period. 1.7.8. Go quietly into the night, maybe that's what I was trying to say. Definition. No, you never go quietly into the night. You fight, right? Isn't that like a poem? Fight the dying of the day or something? Definition of a vertical asymptote. And basically the poor man's version of this is if you've got an infinite limit as you approach a number, you've got an asymptote. You got a vertical asymptote. We'll talk about horizontal asymptotes later on. So the line x equals a is a vertical asymptote of the graph of the function f if at least one of the following is true. If any approach, left or right, gives you an increase or decrease without bound, you've got a vertical asymptote. So there's 4 ways to say that. 1, if as you approach a from the right, f of x increases without bound, vertical asymptote. If as you approach a from the right, f decreases without bound, you've got a vertical asymptote. If as you approach a from the left, f of x increases without bound, you've got a vertical asymptote. And finally, if as you approach a from the left, f decreases without bound, you've got a vertical asymptote. Whew. Didn't quite make it before pod time, but 5 minutes into pod time, I'll take that every day of the week, twice on Sundays. Your remaining 14 minutes should be spent furiously completing your 2 homework assignments, 1.6 and 1.7, both to be turned in with just spectacular work shown at the beginning of class on Thursday. Questions, thoughts, feelings? One note about the 1.6 homework that did come up. Everyone mark it down. Question 25 on 1.6. Gives you the limit x approaches 2, I think, of it looks like that. 0, 1, round 12. The heck is that? WTH. WTH, that's called the greatest integer function. And I think kind of a verbal version of this, but you want to mention back in section 1.1, when we reviewed functions, This is on page 9 in your book. I'm gonna write that down. Page 9. Introduce you to the greatest integer function. In fact, I'm gonna turn to page 9. This is kind of gonna be disruptive. Because it's really the graph that you care about in 1.6. What the greatest integer function does. Use a verbatim definition. No, let's tell you. If you put, we call this f of x. F of 2 gives you 2. Cool. F of 2.1 gives you 2. F of 2.87 gives you 2. F of 2.99999999999 gives you 2. What do you think up 3 gives you? How about every decimal addition to 3 until you get 4? Okay, so it just kind of kicks you back to the nearest integer that is less than that number. Okay, so your graph ends up looking kind of funky. Again, on page 9, where it looks like a staircase. Kind of cool, actually. So like from 1 to 2, all of those intermediate values get kicked back to 1 until you get to 2, then you kick up to 2 for all those values, then you kick up to 3. So that's a kind of a fun function to consider limits on because quick finger test. Oh, if you approach 2, I don't think anyone like that. Kind of a fun one, I don't know. I don't off the top of my head know the use of that function. I'm sure it has a use of, I haven't made it up, but that's 25 on 1.6. Oh, I'm still recording over there. Sorry, whoever is wondering if they need to be paying attention now, you don't. Hopefully you zoomed out, zoned out. I'm gonna stop this. Stop video, stop video. Or not stop video, I want to stop the recording. End mean for all, later.